Good morning, all of you. This is Dr. Nageswara Rao, Assistant Professor of Physics, SRR and Xavier Government Degree College, Autonomous, Vijayawada. Today, we will discuss about superconductivity. We know, according to electrical conductivity, materials classified into three types. One is conductors, second one is insulators, and third one is semiconductors. Conductors is nothing but at room temperature, the electricity will flow easily. Insulators is nothing but there is no current flow through them at room temperatures, just like wood, paper, plastic, pingani, etc. In case of semiconductors, at room temperature, the electricity will flow partially. Examples are silicon and germanium and some of the metal oxides. Now, what is superconductivity? Superconductivity is nothing but it is something different from the ordinary conductors whose resistance drops to zero below to a very low temperature. This temperature is called critical temperature. It means that when the material whose temperature decreases, when its temperature below some of the temperature, its resistance drops to zero. This phenomena is called superconductivity, whose resistance drops to zero are called superconductors. But in case of ordinary conductors, the resistance gradually decreases, but not it is going to zero. That is main difference between ordinary conductors and superconductors. This temperature is called critical temperature. So a superconductor can conduct electricity with no resistance is nothing but there is no heat losses. We know the heat liberated when the current is passing through the resistance is Q is equal to I square RT. Most of the instruments are working in this principle. For example, iron box, where the resistance is very, very high are of the iron box. So that when resistance is high is nothing but the heat liberated is also very high. When resistance is very high, the heat liberated is very high. This is the principle behind the iron box. Not only that, incandescent bulb also, we will use a tungsten filament in bulbs. It contains high resistance and very, very high melting point also. So that when the current is passing through that resistance, the energy will be liberated. That is according to the formula Q is equal to I square RT. So when we touch the bulb, the heat will increase, the temperature will increase. But of course, not only heat energy, some light energy is also will be released by tungsten filament. So in which when the resistance is zero, then what happens? According to this principle, when resistance is zero, the liberation of heat is also zero. So this is very, very much useful for applications nowadays. So when at room temperature, if the conductor is discovered, there is a tremendous changes occurs in industries. So that is at below this critical temperature, the temperature is the resistance zero. If this critical temperature is room temperature, which the success is very, very good. When I observe this graph, ordinary metal, that is ordinary conductor, the resistance decreases like this when the temperature decreases. But in superconductor, when the temperature decreases, initially the resistance decreases exponentially like this. But at some of the temperature, the resistance goes to zero. This temperature is called critical temperature. So that is main difference between ordinary conductor and superconductor. So these a superconductor is defined as substance that offers no resistance to the electric current when it becomes colder than a critical temperature. Of course, some of the examples of these superconductors are aluminum, magnesium diboride, niobium, copper oxide, and yttrium barium are some of the examples of superconductors up to now our scientists discovered. These substances superconduct at temperature below the critical temperature. What is critical temperature? When the temperature of the substances decreases at certain temperature, the resistance of the material is falls to zero. Such temperature is called critical temperature. Up to now, in 1986, the critical temperature obtained is 23 Kelvin. That's very, very low temperature when compared with the room temperature, that is 28 degrees Celsius or 30 degrees Celsius. In 1920, at a room temperature, one of the superconductor was discovered by taking carbon, hydrogen, and sulfur, but at the pressure of 270 gigapascal. So at very, very high pressure, some of the scientists identified the superconductor at a room temperature. But we required at 1 atmosphere, if we discover the superconductor at a room temperature, there is a tremendous changes will occur in future in our industry. And one more experimental result discovered in this superconductivity is critical magnetic field. We know when the superconductor whose temperature is less than critical temperature, whose resistance is zero, that is nothing but superconducting state. When it is in superconducting state, if it is kept in the magnetic field and whose magnetic field increases, at certain intensity of magnetic field, it loses its superconductivity. It is nothing but the superconductor changes as ordinary conductor. Such magnetic field intensity is called critical magnetic field. So you see here, if an increasing magnetic field is applied to a superconductor at a room temperature, or critical temperature, then the material will be make a transition from the superconducting state to normal state, and which field as well as defined strength. This magnetic field is called critical magnetic field, will be represented by HC. So if this field is reduced, when the temperature held constant, the material returns to superconducting state at the same critical field strength HC. But above this critical temperature, even though the temperature reduced to very, very small, we cannot get the superconducting state. So the superconducting state cannot exist in the presence of magnetic field greater than critical value, even at absolute zero temperature. Actually, there are two types of superconductors we have. One is type 1 superconductor and the second one is type 2 superconductor. Actually, in type 1 superconductor shows one critical magnetic field only, but type 2 superconductor shows two critical magnetic fields. One at the onset of a mixed superconducting state and a normal state, and one where superconductivity ceases. So the relation for critical magnetic field with temperature is Hc is equal to H naught into 1 minus T by Tc whole square. So this shows the different type of superconductors with different critical magnetic field. You see here in this first diagram, this is a type of superconductor where magnetic field decreases. At this Hc, the superconducting state changes into the normal state. If this magnetic field decreases from critical magnetic field to ordinary field that's less than critical magnetic field, this superconducting state occurs. But in case of type 2 superconductors, there is two critical magnetic field. We are observing this Hc1 and Hc2. So this is normal conducting state. This is Sc is nothing but superconducting state. In between them, there is a mixture of normal and superconducting state. So that In type 2 superconductors, we have two critical magnetic field. One of the experimental phenomena observed in this superconductivity is Meissner effect. It is discovered by Meissner. What is this? When this superconducting material kept in a magnetic field, these lines of forces of magnetic field expelled. So the Meissner effect is the expulsion of magnetic field from a superconductor during its transition to the superconducting state, when it is cooled below the critical temperature. So the expression will be repel a nearby magnet. This is we see in the diagram. When the temperature is more than critical temperature, it is nothing but this material is ordinary metal. There is no superconducting state. In such cases, the magnetic line of forces which is passing through the magnetic material, it is nothing but it is these rays penetrate through the material. That is, maybe it is metal, it is ordinary conductor, or maybe insulator or semiconductor. But in this case, if the temperature is less than Tc, is nothing but this material is superconductor. If this is superconducting state, the magnetic lines or forces are expulsed. So there is expulsion of magnetic field occurs. It shows that this material, superconductor, is a diamagnetic material. It is nothing but when ordinary metal is changes into the superconducting state, it changes from paramagnetic material to the diamagnetic material. Or ferromagnetic material is changes into the diamagnetic material. This is the special property of the superconducting state. This phenomena is called Meissner effect. So the Meissner effect says that expulsion of magnetic field from a superconductor during its transition to the superconducting state. Actually, this is discovered by Meissner and also Feld in 1933. They discovered. And these samples in the presence of applied magnetic field were cooled below their superconducting transition temperature, whereupon these samples cancel near all interior magnetic fields. The superconductors in the Meissner effect exhibit perfect diamagnetism because all the magnetic lines of forces are expelled. So this is a perfect diamagnetic material. Of course, this effect is used in high-speed trains. Nowadays we are using that is super speed trains, bullet trains. So in these cases, we apply this diamagnetic program. Then what happens? There is repulsive force between track and the wheels. Due to this repulsive force, the frictional force decreases. Due to this decrease in the frictional force between track and wheel, the speed of the train increases. Now we are using, now some of the countries are projecting, that is high-speed trains, that is bullet trains. The principle behind them is Meissner effect. And one more principle was observed in the experimental procedure of superconductivity is isotope effect. Isotope effect is nothing but the critical temperature of superconductor where is it isotopic mass. We know isotopes. Isotopes is nothing but there is same atomic number but different mass number. So in such cases, if the isotopic masses changes, the critical temperature of the superconductivity is also changes. For any given material, the transition temperature, that is critical temperature, is inversely proportional to square root of the atomic mass. This phenomena is called isotope effect. So how can we write? This critical temperature, Tc, is inversely proportional to, that is nothing but 1 by square root of the atomic mass, that is m to the power half, or root of m. This is called isotope effect. So then we may write that is m to the power half into Tc is equal to constant, where m is the atomic mass or isotopic mass and Tc is the critical temperature. So from this equation we conclude that when the atomic mass is more, the critical temperature is less because both of them are inversely proportional. For heavier isotopic mass decreases the lattice vibration, that is the reason behind that. This indicates that superconductivity is due to lattice interactions. Thank you very much. These are the some of the experimental results of superconductivity.